I have with me Nic Ilyadis. He is the CTO of the Networking and Infrastructure Group at Broadcom. Nic, thank you very much for joining us.
It's a pleasure to be here. Thank you.
Nic, what, in your opinion, are the biggest unsolved technological challenges in data center networking today?
So one of the challenges is as we scale these large data centers, these cloud data centers, or these service provider data centers, the number of servers are challenging the traditional network topologies that have been built for traditional data centers. So as you have tens of thousands of servers or 40 or 50,000 servers, the network topology to support that in a cost-efficient and high-performance way is very difficult to achieve with yesterday's technology. So today, a lot of our customers, the OEMs that build the networking gear, are looking at this new class of fabric, this flattened network or a fat tree topology, which allows you to continue to add more elements without having to incur higher costs in scaling the network vertically. You scale it horizontally and keep adding elements, just like Lego blocks in a network. The second challenge is how to maintain separation of customers or services or data inside the data center, and being able to maintain multiple virtual domains, tens of thousands of virtual domains that belong to separate customers or separate entities, and keep them from being accessed by individuals that aren't supposed to have access. So kind of the security aspects of data in the network and being able to maintain the virtualization and or separation of customer space between different servers or virtual machines, and how that gets implemented within the network.
Do you think the major makers of data center switching and routing gear are on the correct path to solving these challenges?
I believe they are all aware of this challenge today, and I think several of them are already going down that path. The challenge is that this is a network level solution. It's not a box level solution. So you have to be able to design a set of products that interoperate as together in a systematic way that scales across the entire data center network. And so companies can't just build a box that would go into a network. They have to build a system of boxes that can then be deployed in a manner that scales out in these networks. So I think there's a few companies out there today that are on the right path, and others are starting to realize that they need to go develop these type of products.
Do you think flatter network fabrics, they're very eagerly promoted by the switching industry? That is that the correct kind of the one solution to these problems?
It is
Are there
a
any
solution.
alternatives?
I think for the scaled out data centers, the ones that are in the 10,000 to 50,000 servers, I think this is the most economical and high performance way to do it, because it provides you low latency and redundancy in one architecture. For smaller data centers, I think classical architecture still work, the tiered networks, and especially in heterogeneous environments where you may have some legacy equipment and some new equipment, mix and matching it, and it works out well. But if you're doing a greenfield data center build out where you're basically deploying all new servers and all new switching equipment, a fat tree topology, a flattened network, provides the most cost-effective means to do this. Plus, it provides the highest bandwidth and lowest latency between servers, because a lot of the applications today in the data center are not just client-server, they're server-to-server applications like Hadoop, which creates lots of east-west traffic, and this architecture does allow a very efficient transfer of data between servers in that application.
Do you buy into the message that it was virtualization that brought on these issues of throughput capacity and management complexity, to the extent that data center operators need to completely rethink the way networking is done today?
So virtualization has done a good job of squeezing efficiency out of servers, meaning that servers can now be fully loaded in terms of how much applications they're running or what their load is, but that in turn puts load on the network. So now where the server was running one or two apps, you may not have had the network pipe fully utilized, but when the server now has multiple virtual machines fully utilizing its resources, the network gets saturated. So virtualization has put stresses on the actual networking connection to provide the highest bandwidth possible. now managing all those virtual machines, because those virtual machines now become entities on the network versus the server being the managed entity. Now the virtual machine is the managed entity, and if you have dozens or more virtual machines per server, your networking address space is now exploded because each one of those has its own MAC address and has to be individually managed. So I think there's a new class of management software that has to be developed or evolved to be able to manage the fact that your edge of the network is no longer the physical port on the switch or the physical port on a server, but it's actually the virtual port inside the server that's being addressed. And the technologies coming out of the IEEE in terms of standards are addressing this. And you'll see adoption and rollout of this over the next 18 months to 2 years of equipment that actually is knowledgeable of what's going on inside the server's virtual switch and be able to address those virtual machines in a very efficient manner, and then allow management tools to be able to accommodate that new model. So I think 18 months to 2 years from now, you'll see much richer management tools to accommodate that type of density that we're seeing now.
Do network fabrics create a special challenge for chip makers like Broadcom? And if yes, what is that challenge?
They definitely create challenges because we are integrating more and more ports, more and more functions per networking device, and now we're seeing devices that are of the same scale as the processors themselves. So in the past, where you would have a CPU within a server that was generating 50 or 100 watts or more, you now have switching elements that are in that same class of power. So we're spending a lot of time designing power efficiency mechanisms inside our chips so that we can now cool power them efficiently and then power them down during idle periods. So a lot of innovation is going into the power reduction mechanisms in the networking devices that were probably done in the processor chips several generations ago. So we're now in that same scale of density, billions of transistors per device, 64 10 gigabit ports, or a fabric element that can support a terabit of switching. The power that utilizes is now become significant. So the amount of energy being consumed by the network now starts matching the amount of energy being consumed by the server themselves. So a lot of engineering has to go into how to make that network as power efficient as possible, and we are innovating in several different ways there. Energy efficient Ethernet is the industry's latest standard to address this, but we're also developing technologies that go deeper into the chip to actually power down subsystems during idle periods to save power and reduce the energy consumption.
Nic, thank you very much.
Thank you.